Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to work through an example of applying the work energy theorem when a rotational kinetic energy is involved. So what we're looking at here is we've got this, imagine this giant pulley here, this 30 centimeter radius, 10 kilogram pulley is supported here by these two frames and free to rotate. And this blue mass here, 5 kilograms, is hung from the end of it for whatever reason. All right. Imagine this system is released from rest. The blue mass starts accelerating down, and what we're going to try to do ultimately is calculate the time, how long it's going to take this blue mass to before it hits the floor. But we're going to start this using a work energy approach. So when you're applying the work energy theorem, you always want to draw the system at the two different states. So I'm going to call this state 1 here. Right? State 1, the system starts from rest, and this blue mass is 2 meters off the ground. All right. State 2 is going to be just before the blue mass hits the ground. And I'm going to go ahead and kind of copy it. So that's going to be my state 2. It's important to realize it is still connected by the rope. String, whatever it is here. So let me get that still attached. Okay, the intention here is not that the rope broke. That would be a different problem. And it's important to realize in state 2, you notice that there's some daylight there, and that's deliberate. This is, state 2 is just before impact. And at state 2, this thing would be moving, so it would have a velocity vector that would point down. Oops. And I'm just going to call it V. We could call it V2, which I do in a lot of my videos, but in this problem, the V1 is 0, so I don't really feel I need the subscript on that velocity vector. All right, so now what I'm going to do is write out the theorem of work and energy. All right, PE1 plus KE1 plus work equals PE2 plus KE2. And what I'm going to do is just go through this thing line by line. Or I'm sorry, term by term. All right, so the potential energy terms. Now this is, your potential energies depend on your datum. So the first thing we do with a potential energy term is define a datum. I'm going to go ahead and I'll draw this in green. So my PE2 is going to be measured from here. And I'm going to make that datum go basically right through this object. All right, so by putting a datum here, what we're saying is that we're basically forcing PE2 to be 0. Now, while I'm at it, I'm talking about position 2 here. This thing is moving in position 2, so it's got a kinetic energy of 1/2 mv squared. If there were another velocity in this problem, I'd probably tack a 2 on there, but because V1 is 0, I'm not going to bother with that subscript. Right. Let's talk about PE1. So at position 1, the blue mass has a gravitational potential energy equal to mgh. It's important to know that this mass is the blue mass here, the 5 kilograms. Now, technically, the pulley has a potential energy with respect to this datum. However, let's just say I put a mass of the pulley, g, times this height. I'll call that capital H for just a moment, where that's the capital H. Well, you're going to have exactly the same term under the PE2, and it's just going to subtract it off anyway. When something is not changing in potential energy, you don't need to worry about it. So I'm just going to have the mgh here for the blue mass. System starts from rest. No external force is acting on the system. Now again, this is a consequence of how I'm defining the system. If I were defining my system as just the pulley, there is in fact a tension right here applied down, and that tension would be doing work as the pulley rotates. If my system were just the blue mass, all right, that tension applied to the blue mass is up. And this tension, as the blue mass moves downward, is doing negative work on the system. But the tension would be the same in both cases, and the distances are the same. If you add those terms up, you get 0. So long story short, as long as I define my system as the pulley and the blue mass, there is no work done on the system. Right? Or I should say there's no work done by external non-conservative forces. The gravitational force does work, but we took that into account with a potential energy. The other force applied to the system while I'm at it is the system is supported here at the pin. So we could put some sort of normal force up, or maybe pin force there we could call it. applied here. But this point doesn't move during this problem, so there's no displacement, so there's no work done. Now, getting back to the right-hand side, the 1/2 mv squared takes into account this animal. However, in addition to that, at position 2, the pulley is also rotating. It has what we would call an angular velocity. So under the KE2 term, we also have a kinetic energy for the pulley. And the kinetic energy can be expressed 1/2 I times the angular speed squared. So it's important to realize in this problem, under position 2, there are 2 kinetic energies that need to be considered. I probably should have talked about the pulley back when I put the 1/2 mv squared in, but there it is. I got them both now. 2 kinetic energy terms, one for the mass, the blue mass that's accelerating down, and one for the pulley. All right, I'm going to rewrite this line now, cleaning everything up. So this is going to be mgh equals, all right, 1/2 mv squared plus, all right, now let's take a look at this term, the moment of inertia. If you look up the moment of inertia of a disk, that's the closest geometry to this pulley, the moment of inertia of a disk is 1/2 mr squared. So I'm going to write this up here, 1/2 mr squared. When I take the 1/2 and multiply by this 1/2, I'm now going to have a 1/4. The mass is going to be the mass of the pulley, and then times the angular speed squared. Okay, so now we have an equation here, but it's got 2 unknowns. We've got this v and we've got this angular velocity. Right? They're linked together, though. They're linked by the fact that this rope doesn't change. And the velocity here is the same as the velocity of any point on the rope, which is the same as the velocity right here on that pulley. I'm going to draw a velocity vector there. And here is some radius. And these are linked by v equals r times the angular velocity. And again, you can go back and watch my video about the radian in rotational motion to see where that's coming from. So the angular velocity can be written v over r. So I'm going to rewrite this equation one more time. mgh equals 1/2 mv squared plus 1/4 mass of the pulley times, now this can be written v over r squared. Now, when we look this over now, this only has one unknown in it, the v. I'm going to go ahead and put numerical values in this. All right, so this mgh, and because I don't have room here, I'm going to put note consistent units. So this mgh is going to be 5 times 9.8 times 2 equals. Now, another thing I'm going to do is I'm going to go ahead and factor this v squared out. And then this term would be m over 2. That's going to be 5/2 plus. Now when we factor a v squared out of here, we're still going to have mass of the pulley, which is 10. And if we look carefully, we end up with 4r squared in the bottom. So I'm going to put 4 times 0.3, and that's squared. I'm going to look at that very carefully. The v squared is factored out. We're left with mass of the pulley up top and 4r squared in the bottom. Yep, that looks good. I'm going to take a moment now. I'm just going to pause the video while I calculate a value for v, because again, I've got more work to do and I don't want this to get too long, so I'll be right back. All right, folks, so I'm back, and I got about 1.8 meter per second for that v final. Hopefully it's right. I'm going to ask the viewer here to double check that, solve that equation for v. All right, so, whoops. The next part of this here, is the time part. So what I need to do here is I need to get rid of a bunch of this work, because now I'm going to do the motion study for the problem. I'll leave that 1.8 there, so I don't need any of this anymore. All right, and what I'm going to do now is draw myself a velocity graph. For those of you who've been following maybe some of my videos or have had me in class, you know that I just love graphs. So to study the motion of this particle, what I'm going to do is I am going to sketch a graph of velocity versus time. I'm going to go ahead and do down positive for this video. And if we do down positive, at t equals 0, this thing's velocity is 0. So the first point on here is 0, 0, because it started from rest. And then sometime later here in position 2, right, we don't know the time, but it suffice to say it has to be some number. We know that the velocity is 1.8 meter per second. So on this graph, that's going to put us here. Now, from experience in writing Newton's second law equations, we know that this acceleration is going to be constant because the net force acting on the system is constant. That's going to give us a linear graph. And then, as far as this velocity graph is concerned, we know this is a 2-meter displacement. And that 2 meters is going to be given by this triangle, that triangular area. 1/2, the base is t, unknown, and the height is 1.8 meter per second. So what I'm going to do now is go ahead and solve for that time. Give me a moment. And I got 2.2 seconds out of that approximately. And while I'm at it, I'm going to go ahead and get the acceleration of this mass. And again, acceleration is rate that velocity changes. So on a velocity versus time graph, that's going to be slope, right? And that's going to be rise over run. So that's going to be, let's see, 1.8 meter per second over 2.2 seconds. I get about 0.82 meter per second squared for the acceleration of the system. Now, again, this was done using a work energy analysis. We could have also drawn a free body of this mass, which would have a tension up and a gravitational force down. We could have written a Newton's second law equation for it. We could have drew a free body of the pulley, written a rotational Newton's second law equation where torque equals I alpha. And we could have solved that system for the tension and the acceleration, right? That would have been an alternative approach. Here we used work energy instead to find the velocity, and then we can get the acceleration from the velocity graph. So anyway, I hope this video helps demonstrate how to apply or how to incorporate rotation into the work energy theorem. Have a great day.